Thanks, Jeremy, for the invitation. It's a pleasure to speak at this online conference, my first online conference. And thanks a lot for organizing the schedule in this way, because actually I'm very happy to speak after Benjamin's talk. So I should mention I'm not a symplectic geometer, but I'm very much interested in toric degenerations, and this is exactly where I think we will intersect now. So I'm going to give you first a motivation for my talk. So I like to study toric degenerations of flag varieties. For this talk, it's going to be flag varieties of type A, so SLN mod the Borel subgroup. And there are many approaches to construct toric degenerations or to study them. And for this talk, I will focus on two of them. So one is considering the flag variety as a quotient of an algebraic group, so of SLN in this tape, and then use representation theory to construct toric degenerations, which is pretty much along the lines of the toric degenerations we just saw in Benjamin's talk. And then the second approach I'm going to tell you about is taking the flag variety as a compactified cluster variety and use the cluster structure, or more precisely cluster duality, to construct toric degenerations of the flag variety. So let's get into it. The motivation here, or the question, is how are these two related? So I'm going to quickly set up my notation for SLN. Well, I fix the Borel subgroup to be upper triangular matrices and T the torus diagonal matrices. I further need a subgroup U that was denoted by capital N in Benjamin's talk of upper triangular matrices with ones in the diagonal. Now, capital N for me is going to be the dimension of the flag variety. Then I fix the weight lattice that I get from fixing the torus. It's isomorphic to z to the n minus 1, where the basis for this isomorphism that I choose is the basis of fundamental weights, omega 1 to omega n minus 1. And then I have the dominant Weil chamber that is the positive orthant in this lattice. Further, I will need the symmetric group Sn, which appears here as the Weil group of SLN, and it's generated by simple reflections Si at swap I and I plus 1. And now by W0, I will denote the longest word in the symmetric group, and every reduced expression of W0, I will write it with this underline. So this is just a sequence, a word in the generators Si that is of length N, capital N. Okay, so then let's get started with the string polytopes. For every reduced expression of the longest word now, I can define a string cone, or a weighted string cone more precisely. So this is some cone that lives in the product of r to the n, and again being the dimension of the flag variety, and r to the n minus 1, where the second copy comes from the dominant Weil chamber. And this is exactly one of the cones that we've seen in Benjamin's talk before. It's a nice example of those. And we've also already seen, actually, we can slice these cones over integer points. So I can now take a hyperplane in this product of two vector spaces just by fixing lambda, an integral dominant weight, in the second copy. And I can take a slice of my weighted string cone, and this will define for me a string polytope. So I'm sorry, this should be the curly C as well. So now for every dominant integral weight, and for every reduced expression of the longest word, I get a string polytope. And these have been introduced by Littelmann and Berenstein Zelevinsky more generally for semi-simple algebraic groups. And it has been shown that they arise in the setting of evaluations that Benjamin told us about, then proven by Cave and Fourier and Littelmann. So one example, if you're not familiar with string polytopes, if we choose a very nice reduced expression for the longest word here that starts with S1, then S2, S1, S3, S2, S1, and so on until Sn minus 1 to S1, then the string polytope associated to this word for every dominant integral weight is isomorphic or unimodular equivalent to the Gelfand Zeitlin polytope for the same weight. Now, why are these string polytopes interesting? Well, I already mentioned they show up in the setting of evaluation, so you can construct toric degenerations using the string polytopes. Littelmann already showed that, or that's actually the reason why he introduced them, that the integral points in these polytopes, they parameterize bases for the irreducible highest weight representations of SLN, and then more generally, bases of Lustig-Stuhl canonical, they parameterize Lustig-Stuhl canonical bases. And as already Benjamin mentioned already, for every integral dominant weight that is additionally supported on every fundamental weight, we get an embedding of SLN mod B into a projective space, and the homogeneous coordinate ring is a direct sum of duals of representation. So the string polytopes, moreover, parameterize a vector space basis of my homogeneous coordinate ring here. And this is exactly the philosophy to have in mind now that was used then by Caldero to construct toric degenerations of the flag variety SLN mod B to the toric variety that is defined or associated with the string polytope. So what's the theorem here? We fix a reduced expression of the longest word. We choose an integral dominant weight supported in all fundamental weights, and then we get a toric degeneration of SLN mod B, the flag variety, to a toric variety. Now, this result has been generalized. First of all, Caldero already shows it also for Schubert varieties, so that's true more generally. It's also true for not only SLN, but semi-simple algebraic groups. And then it has been generalized to spherical varieties by Alexeyev and Brion, and so on. So this is the first part of the story that you're probably quite familiar with. Now, the second part of the story I want to tell you here is about cluster varieties, and I'm going to go through some details of the definition of a cluster variety, because I don't assume that too many people are very familiar with it. So in general, to define a cluster variety, I need to set up some notation. I will start with a lattice n that is isomorphic to z to the m, and I fix additionally some bases as 0 that can be the standard basis of the lattice. And then dually, I get a dual lattice that is also isomorphic to z to the m, which I will denote by m, and I get the associated dual basis. Now, the lattice, both lattices define complex algebraic tori. The first one associated to n is then spec of the Laurent polynomials in monomials whose exponents are exactly these basis elements, plus minus these basis elements. And I want to emphasize this here because it's going to be important for me to fix a basis in a second. So this is why I captured it also in the notation. So Tn, all these tori are isomorphic if I choose different bases here, but I indicate the basis here anyway. So dually, I get a dual torus that is C star tensored with the dual lattice M. Now, with this information in place and some additional information, some additional data that I hide from you now because it's quite technical, but that's essentially all I need to define a cluster variety. So a cluster variety is a schema over the complex numbers that is glued from complex tori. So I can write it as, first of all, as just a union of a bunch of complex tori. And there's a specific procedure that, that tells me how many tori I get and how I glue them, etc. And because I naturally have a lattice and a dual lattice, a torus and a dual torus, I get cluster varieties of two flavors, one being denoted by A and the other being denoted by X. So as I already mentioned, like all the copies of the tori, they are isomorphic, but I glue them together in a kind of a weird way. So the idea of this gluing is I take my basis as 0, and then from this additional data that I fix before I can define a cluster variety, that tells me how I can construct a new basis of the lattice from the given one by applying certain pseudo-reflections. And then these pseudo-reflections induce for me also the gluing morphism between two copies of the torus. And when I fix this on the basis E1 to EM for my lattice N, then the dual basis changes accordingly, and that fixes for me the gluing on the dual side of the picture. Now, if I now have such a cluster variety, usually these are objects that appear that, I mean, for example, in this setting, we will see how the base affine space SLN mod U appears as a cluster variety, but it is not actually a cluster variety, but a partial compactification of it. So in particular, if I start here with my set, with my basis, I could clarify from the start that I want to always keep a certain part of the basis fixed. So I would apply pseudo-reflections, but after applying the pseudo-reflections, I would still have some of the basis elements that I had before. And if I do that, that has as a consequence that I actually never have to look at the elements, the monomials with minus that basis element as an exponent. So I can let all these functions, I can let them vanish because I never use the inverse of this function. And then this defines for me a divisor on the cluster variety, and I can partially compactify it by adding this divisor. So, and if I do that, more interestingly, this partial compactification defines for me a superpotential on the dual cluster variety. So this is a function on the dual cluster variety that is a sum of certain theta functions, and all of this comes from is written like in the language of mirror symmetry. This is quite a nice example of mirror symmetry of Calabi-Yau varieties or La-Calabi-Yau varieties. So I get this potential function that corresponds to my divisor, and the only thing you can see how they are related right now is that the summands of my superpotential correspond to the components of my divisor. And well, this potential is really what we're interested in this case, because of the following. So we can now tropicalize this potential, and that will define for us a convex cone. So what does tropicalizing this potential mean? So for example, that my potential could have only two summands, two monomials. And in some bases, it could be expressed like this. And when I tropicalize that, I simply replace multiplication by addition, and the addition in my expression of the superpotential by taking the minimum. So every monomial here defines for me a hyperplane, defining hyperplane, and then the addition only translates to minimum. So in particular, in the tropicalization, if I have a point in this example in R2, it would have to satisfy two inequalities. And well, I kind of jumped a bit ahead here of having already the superpotential expressed in some coordinates, because if I just look at the superpotential on my X cluster variety, I don't have a fixed coordinate system. But what I can do is I can go to one chart, one of these torus patches of the cluster variety, and then I can express the superpotential in those coordinates and tropicalize it there. And now these tropicalized superpotentials will define for us toric degenerations as well. So that's a construction that was given by Gross Hacking Keel and Kontsevich that tells us now under some nice technical assumptions that will be fulfilled for the case where we're going to apply this construction to. For every seed, we get a toric degeneration of the compactified A cluster variety to the toric variety associated with this convex cone. And the construction here is quite similar to the one using valuation. So this is in the end nothing else but the same Rees algebra construction that Benjamin already mentioned in his talk. So let's see how flag varieties appear in this setting. So Berenstein, Fromin, and Zelevinsky, or maybe also I should mention Fock and Goncharov, due to their work, we know that the base affine space SLN mod U is isomorphic to a compactification of an A-type cluster variety. Then also Timothy McGee, that's a student of Sean Keel, he further showed in some paper that all the technical assumptions we need to apply this Gross Hacking Keel construction are satisfied. So, and then using also Berenstein, Fomin, and Zelevinsky, we know moreover that when we fix now a reduced expression of the longest word, this actually defines a seed in the torus of, or in a torus seed, a cluster chart in the atlas of the cluster variety A. And that's like just a combinatorial procedure that you do to get the information of a seed out of a reduced word. So now we have like kind of an overlap in these two constructions. We have one toric degeneration associated to every seed using the Gross Hacking Keel Kontsevich machinery, and we have one toric degeneration associated to every reduced expression, and then we have seeds that correspond to reduced expression. So this is naturally the place where we look for identifying these toric degenerations. And this is exactly what we show. So if you fix the reduced expression of the longest element, then there's a unimodular equivalence between the weighted string cone and the superpotential cone, or the cone that is the tropicalized superpotential in that specific set of coordinates. Now, so far, this is not yet where we want to go, because it's just talking about toric degenerations of the base affine space, but we would rather want to have toric degenerations of the flag variety itself. But that's also possible, because the base affine space here actually it is the universal torsor of the flag variety itself. So in particular, this is a quasi-affine variety, and its coordinate ring is the direct sum of all duals of highest weight representations associated with integral dominant weights. And the flag variety, we've seen that when we embed it into a projective space associated with a representation, then its homogeneous coordinate ring there is a direct sum of the multiples of all irreducible representations associated to multiples with one fixed weight. So in particular, these rings are closely related, and this is how we can pass from the toric degeneration of the base affine space to a toric degeneration of the flag variety. So how does this look like on the level of the polytopes and cones? There is a hyperplane for every dominant integral weight. And if we slice this tropicalized superpotential cone by this hyperplane, we obtain a polytope. And this polytope, if we consider the associated toric variety, that is a toric degeneration of the flag variety. And this all happens within this Gross Hacking Keel Kontsevich construction. So they take care of that for us. And now the second result, or actually just the corollary of the first result, is that moreover, for every reduced expression of the longest word, these two polytopes are unimodular equivalent. So we had the string polytope of Littelmann, Berenstein, Zelevinsky, and its toric degeneration. And now we have the second set of polytopes coming from the tropicalized superpotential, and they are unimodular equivalent whenever I choose here a seed that is associated to the reduced expression. That defines my string polytope. And in particular, unimodular equivalence between these polytopes induces for me an isomorphism between the associated toric varieties. So let me summarize maybe what's going on here. So I started with a reduced expression of the longest element in the Weil group of SLN. That defines for me a cluster chart by just doing some combinatorial tricks. But it also defines for me a weighted string cone and a string polytope associated for every dominant integral weight lambda. Now, if I take the expression of the superpotential in the corresponding chart, that is the seed associated with a reduced word and its tropicalization, then I get isomorphisms between the cones, that's the weighted string cone, and the tropicalized superpotential, and as well between the polytopes. Oh, I'm sorry, there's some lambda missing here. So this is the isomorphism between the polytopes, and then an isomorphism between the toric varieties. And I think I really finished. I will really finish early. I just have one bonus slide that I put after the references because I wasn't sure how I'm going to make with time. And that is an example for you for SL4. So for SL4, the cluster structure has only 14 charts. And you should think of this graph as being representing all the torus charts I have for the base affine space, and these two open ends here should be connected. So in this case, actually, I can express everything in terms of Plücker coordinates. So I can choose the Plücker embedding for the flag variety, and then every seed or every set of coordinates of a torus chart will contain 6 Plücker coordinates that are always fixed and additional 3 Plücker coordinates that I've written into these bubbles. And now there's only one extra variable showing up, x, that is showing up as a variable or a coordinate in one of the torus charts, but it's not a Plücker coordinate. And so these 14, they are related like this. So when I perform a mutation, or when I go from one torus to another, when I perform one of these pseudo reflections on the lattice basis, I change from one of these bubbles to an adjacent one. And I do that in such a way that actually in the coordinate system, I always just replace one coordinate by another. So for example, passing from this bubble on the top that contains the Plücker coordinates P2, P3, and P23 to this bubble, I replaced the cluster variable or coordinate here, P23, by the coordinate x. And the pink, the seeds here that are marked in pink are the ones that correspond to reduced expressions. So for these seeds, if I go to one of those and I compute the superpotential and the tropicalization in that seed, that is going to be the same, or unimodularly equivalent to the string polytope I can associate to that seed. But this picture, because it's quite small, like n equals 4 is quite small, it's also a bit misleading. Because here we only have finitely many seeds. But as soon as our n grows, actually we just have one more case, that is n equals to 5, where we have finitely many seeds, and beyond that we have infinitely many seeds. So in particular, using this Gross Hacking Keel Kontsevich construction for large n, we get an infinite number of toric degenerations for the flag variety, while for string polytopes we always have as many as the number of reduced expressions. But any one of these toric degenerations, these infinitely many, can also be described using the language of valuations and the Riesz algebras. So yeah, that's it. That's I think I would just label for you the references, and thanks a lot for your attention.